So you should see the main document now, which is at hbiostat.org/rflow, which I think was in the announcement that Ryan sent around. Now, Quarto is a system that if you have things written in R Markdown, they will almost work just as they are, but it gives you a lot of other things, and it's really a unifying thing. It's really easy to learn. There's a lot of online material, tremendous documentation. Why is it that we really think Quarto is the way to go instead of R Markdown? Well, it's because it's multilingual. You can mix Python with R. But to me, an even bigger reason is that it's multi-platform. So if you've looked at the R world, you'll know if you want to use R Markdown to do a blog site, you need to use the blogdown package. You need to do something different for a regular website, and something different for a book, and something different for a report. Whereas with Quarto, it's just one thing. And so whether you're doing a report, an ebook, a website, or a blog, it's just Quarto. And so you use one syntax and it translates to all these other systems. And I may show you later what a blog looks like that's using Quarto, but I've converted all of my online material to using Quarto, which was really not that hard to do. So most of what we're going to be talking about in our 2 hours today is not really Quarto, because that Quarto is actually so easy to learn, but I will show you some special features and extensions, but we're really going to be talking more about coding and good coding practice. Now, as you probably have seen some of the battles that go on between tidyverse and the non-tidyverse, it's actually one of the biggest arguments. It's probably by far the biggest argument in R. It's equivalent to the Bayesian frequentist debate in statistics. So it's created a real dichotomy, and I think that's a shame. And the main reason I say that is not what people expect. It's that the people who are advocating tidyverse are misleading us to some extent in that they've implied that it's a way to get introduced to R. And Norm Matloff and others have written about in detail how this actually does not serve people's needs, because it makes it actually harder to learn the easy things that are built into R. And so Norm Matloff has argued in various blog articles that learning base R first is really a good idea. And so I've gone these 31 years without using any tidyverse, and I've looked at a lot of work by a lot of staff and a lot of students, and the ones that use tidyverse almost exclusively, I see them running into problems doing things that are not standard things. And these problems are very real. So I'm seeing an inefficiency in using tidyverse. So I do have that bias that some of you will definitely disagree with, but I hope you'll keep an open mind for what we're going to go through today, because I think once you get exposed to the data table package in R, if you haven't been exposed to it before, you'll see it opens up a totally new way to think about things that's very natural and ultimately far easier than tidyverse, and it also runs much faster. So we'll get into some of those controversial elements today. And I do want to point out, if you look at the code icon here at the top of a screen and you click on that, you'll see the Quarto raw stuff. So if you wonder how something was done, just click on that and it's all here. So you see the diagram. You'll see a preface, which is an unnumbered section. Then you see regular text. You'll see a table, and you'll see a table that has cross-references in it. So these are sections in the rest of the ebook, and those section numbers are brought into this table using this cross-reference system. And you see this is markup for Quarto. This is a callout node that defaults to being collapsed. And so when we look at the bottom of that, you'll see this is collapsed, and I click on it and it pops up. So that was what that little bit of markup does. But what are we going to talk about overall? Well, our workflow is about many different things, and these are all things that I found really are sort of every week occurrences, the sort of things that we're dealing with data all the time, especially when we're going to do analysis or graphics. So there's a lot of data processing, learning about the data as a whole. Of course, before that, there's importing the data. And what we're going to spend some time on is annotating data to make the data more useful after you've imported it. So we're going to be looking at data dictionaries and using data dictionaries to assist in coding. And we'll talk some about report formatting, including some particulars about Quarto. And then we get into a lot of the processing, like how to do descriptive statistics, univariate or simple stratification, how to do analysis. And so one of our themes here is going to be staying very close to the data in doing descriptive analyses and trying to avoid tables to the extent possible. And that's especially applicable when you have continuous variables. And so we're not really going to talk about formal analysis today, but we're going to talk about more descriptive analysis. And then there's some other topics, if we have time at the end, to talk about caching, parallel computing, and simulation, some code examples, how to make those things easy to do. So that's the broad view of what we'll be talking about. And I want to encourage anyone on to speak up at any time. Just activate your microphone and your video, or put a question in chat, which Ryan will be watching for. I really love interruptions, so it'd be good to interrupt as we go while we're on a certain topic, because we do cover a lot of different topics in this session. Now, there is a detailed case study in the ebook, and so we're going to go through a few things. I'm just going to overview them because we get into them more detail when we get to certain chapters. Some recoding, annotation, data snapshot, and some analysis, including univariate analysis and descriptive association analysis. You see the sections here. You have this live table of contents. You can click on that as needed. And so there's an introduction telling what we're doing and where the data set came from. This is a very new version of the famous Titanic data set. This version is called Titanic 5. A lot of my older material will use Titanic 3. So there's a section on importing the Titanic data, which exists as an Excel spreadsheet and as a CSV file. And this is a good example of what problems Excel causes. There's some data in the spreadsheet that are mixtures of, say, left justified and right justified numbers. And Excel actually has a bug in that particular setting, and there's no way to import the data and to have it faithfully rendered outside of Excel. As long as you stay inside Excel, it works. But there's no way to export that in a faithful way because of this little error that Excel has. So in this particular case, I showed how to read the Excel file, but also how to read the CSV file, which is what we're really going to analyze. So it's real easy in R to read files that are not local, but they're on the web. And csv.get is in the hmisc package. So I'm getting access to the hmisc package with the require command. I'm getting access to a lot of new scripts that are on GitHub with the getrs command, which is in the latest version of hmisc on CRAN, the repository. And then I'm going to download the Excel, because I'm going to at least look at the metadata from Excel. Then I'm going to look at the real data from CSV. I'm going to do a little bit of processing, and I'm going to turn it into a data table. And we'll be talking more about what's the difference between a data table and a data frame, but they're very similar. And one thing weird about data tables, probably the most weird thing, is sometimes you have to tell it you're actually copying, because you might make changes in this data object D. And if you don't just copy it, but you just say D gets T5, less than dash T5, if you just say that, that's going to have D referring to the same place in memory as T5, and any changes in D will be made in T5 also. So this is how in data table you make a clean separate copy if you don't want your changes to be back propagated to the original data table. we're changing the names of one of the variables. We do that with the set names. And we're looking at the starting point of the data. And you see one of the challenging variables is when the Titanic sank in I forget what year, it was like 1913. And if you want to analyze whether those that bought a more expensive ticket had a better chance of getting on a lifeboat, the measurement units were in pounds and shillings, and now I'm temporarily forgetting what the D stands for, pence, I guess. Yeah. And so we're going to have to do some processing to take this one field, which really has three fields in it, and to split it into three things so that we can apply the formula to convert that to pounds as decimal. I think England went to the decimal system for pounds maybe 1960 or 70, something like that. So we're going to read the Excel metadata, which is read correctly. And we're going to do a little bit of renaming things. I'm not going to go through all that right now. But we're going to get into a little bit of recoding, and this tells you what chapter this is expanded upon. So we're going to make something that was a character string be a regular date. A regular date is going to have a format of 4-digit year, and then the month, and then the day. But we started out with month, day, and year, so we're translating that. Now, this is the data table format for creating or changing a variable in place. So this doesn't make any copy of your data, which is very good to know if you had a massive data set. So this DOB is going to be transformed in place without rewriting the whole data set, just changes a little piece of memory. And so that's how you make something officially a date variable. This is how you can process data within a data table. And I'll show you some breakdowns that make this a lot more clear when we get to that chapter. And then we're going to look at some of the data with some initial plots, histograms. We're going to remove some variables by setting them to null. That's how you remove variables in data table. You can also do that with data frames. And then this is the formula we need to evaluate. We have pounds, shillings, and pence, and this is the formula for converting these to pounds as a decimal number. So what we're doing as an example of data munging is these fields are separated and they have this format here. So we're going to separate those into three subfields with string split. We're splitting on the blank as a delimiter. And then the other trick we're going to do here, we have more code than there is processing because we have all kind of data checking going on here. We're going to convert the three subfields into a matrix. And the reason to have that as a 3-column matrix is when you're calculating that formula to translate it into decimal pounds, you can loop over a matrix. So we're going through 3 columns. Every column, we're doing some parsing to see if it was a pound symbol in the subfield, a shilling symbol, or a pence symbol. And then we're going to put the right multipliers in here and add them up by looping over 3 subfields. So that's just an example of getting something out of a variable in a data table or data frame and make it into a matrix. And so once we've done that, we have a function that you can use in many different contexts, pounds to decimal. So don't pay too much attention to the particulars right now, but we have a lot of data checking to make sure the algorithm worked correctly. And we show the inputs and we have the results here. So the next thing we're going to do is to annotate the data. And there's a lot of ways to do that. Now, what do we mean by annotation? There's 3 main kinds of annotation. There's variable labels, there's units of measurement, and there's comments. You could also have some other annotations about particular output formatting that you want for the variable. This is one way to create labels. And you can get those labels from metadata, as I did here from the Excel metadata. And you can get it a variety of other ways that we'll mention later. And then we're going to say HTML of contents of the data table. So this is a function in HMISC that'll give you the metadata. It doesn't handle comments, but it handles these other things. So we have our variable name, the variable label, units of measurement, which were only defined for a few variables. This one's pounds, this one's years. It's a numeric variable, double precision, and there's two missing values for age in the data set. This one is integer, this one is character, and so on. This one has a lot of missing data. And there's 1,309 passengers, 17 variables in the data set. The variable that had the most missings had 1257 missing, which you can see was this variable, the job that the person held, the passenger. So that's what we mean by metadata. And so that metadata really comes into play and is very handy. And you can view the metadata a variety of ways. If you're doing a report, this HTML table will appear right in your report, just like a data table. So that's rendered very naturally. If you want to render it in a browser window, you use something like this. And so I want to show you an example of that. Let's see if I can find out where the stop screen share button is. Right. I'm going to share a different window. So this is an RStudio window. And you can see here that I said require of HMISC to get access to that package. And then I said get RSO rep tools, and that's going to get me access to the HTML view script, which is a function. I'm going to get a different data set. This is a way to get data set off of our department data sets repository. These are fully annotated data sets that are very easy to analyze and especially useful for teaching and statistical methods research. I'm going to save the data set into a short name. This is a data frame, so it's going to make a second copy. And then I'm going to say HTML view of contents of D. And you see that that appears in the viewer window of RStudio. So now you have your metadata, and these things will wrap according to how much width you have. So if you expanded your window, this may be 2 lines instead of 3 lines. And then if you click here, that's a link to the value labels for the sex variables. So you can easily get to the list of values for categorical variables. What's the storage format, the number of missings. And what I did in here, I used the updata function to add units of measurement for one of the variables, heart rate. The units of measurement was beats per minute. So when you see, that's the only one that we bothered to put units on. The units information comes there. So this idea of metadata is very important, because it means you don't have to have quite as much text in your variable names. And it means that you have units of measurement documented and labels. So if you really want to know what the variable means, you would want to look at the label in addition to the name. So this gives you the full definition. And then the units have special purposes, and you'll see these are used automatically in certain contexts. So that when you're making a graph, you're using a scientific format where the units of measurement is in a smaller font than the variable label. So you'll see some contexts and examples where the labels are used automatically, and then this will appear to the right of the label with some space between them, and this will be in a smaller font. So the units of measurement have special use. So does anybody have any question about anything so far? All right, I'm going to get back to where we were. Okay, so that's contents. And now this is where you can do recoding and annotation all in one step. So this is a good example of the update function. I just showed you a little example a moment ago. So this says we're going to rename the variable DOB clean to DOB. And .q is a little function in the HMIS package that just quotes things when needed. So you notice this would normally need to be quoted with a single or double quote. .q is going to automatically put quote marks around that just so you don't have to, which is only relevant if you're renaming a whole lot of variables. But just think of .q as adding quote marks to the right-hand side here. So that is the old name and that's the new name. This is translating to a date. This is creating age from date of birth. This is doing something with missing ages, getting from another source. We're using pounds to decimal to convert price to pounds in decimals. And we're dropping two variables. We don't need to quote them because of .q. And we're giving labels to several variables. Things that have space or special character in them, you have to quote. Otherwise, you can leave the quote marks off. So we're giving a label for age, price, DOB, and so on. And in units of measurement, age is going to be years. Price is going to be the symbol for British pounds. And then update is going to tell you what it did. So you learn what's happening. You may spot that you did something wrong. But you see that it saves a lot of trouble to do everything sort of in one step. Now we get into looking at missing data, and there is this function mischeck in rep tools, reporting tools. And if you say mischeck of the data, you get all kinds of summaries. So it says that there's 10 variables that have no missings in them, and 7 variables have missings. There's 1,309 observations, of which 27 are complete. So there's 27 passengers that did not have any variables missing, and there's 17 variables in all, 10 of which were complete. 10 of the 17 variables never had a missing value. There's an average of 1,257 observations, let's see, per variable, and the mean is 168.4. And I'm sorry, that's the maximum number of missings that any variable had, and the average number of missings was 168. The average number of missing variables per observation was 2.2, and the most number of variables missing at one time was 5. And then you have distributions of number of variables, number of missings per variable, and number of incomplete variables per observation. And then you get a lot of output to understand the patterns and extent of missing. So the number of missings per variable is represented with a simple dot chart. So you can see this job variable had the most fraction of missings, and age had the least. The number of observations, number of missings per observation. So this would be the number of variables that are missing per observation on the average. So it's turning it backwards. The mean number of variables that are missing when another variable is missing. So you can see that when date of death was missing, there was an average of 2.2 other variables happened to be missing on the same passengers. So you're understanding now the clustering of missingness. We'll do that another way. This is the number of observations per variable versus the mean number of other variables missing. So you get more information than was in the last plot. So you're getting a lot more information. And then if you want to see what variables tended to be missing on the same passengers, you can just get this cluster analysis. So this all came from one command in R, and you'll see shortly how that automatically made the tabs in the report. This is sequential exclusion of data due to missingness. So the variable that would exclude you from having observations in analysis the most is the job variable. Once you exclude those, there's still 19 that had missing boat or body bag and so on. And then you can get all combinations of missing with a combination plot. But this is a live plot, so it's using Plotly graphics. And if you hover over something, you'll see a lot more detail. So there were 13 passengers that were missing on date of birth, occupation, and job, all at the same time. And this represents various fractions depending on which denominator you want to use. And you can also look at marginal summaries 2 different ways. So it's useful to have details that pop up when you need them without having a very complicated legend to explain everything that might be needing to show. Then the data overview, we'll see another example of this, but we're getting a snapshot of the whole data table, what's continuous, non-numeric, discrete. Those are the types that are detected from the data. How many distinct values were there for each variable? How much information is in each variable? Now, this means if it's a continuous variable, how much information is it? If it's a numeric variable, how much information is it compared to the information in a continuous variable that has no ties in it? So if you've categorized a continuous variable, you'll see the information measure drop below 1. So this is a low information variable, relatively speaking, because there's only 2 sex values. And so that is going to be a lower powered variable for a lot of analyses compared to a continuous variable like age. How symmetric is the distribution versus, so this would be fairly symmetric. Fairly symmetric, something far from 1 is going to be asymmetric. This is asymmetric because the ratio of males to females is not 1. Number of missings, the least common value, how frequent was the least common value, and what is the most common value. And I think there's some stuff off the screen with the frequency of that. So that's a data snapshot to help you understand the data set as a whole. And you can get plots of that. So what is a plot of the number of distinct values a variable has versus how symmetric its distribution was? So here's a variable that has 300 distinct values that is incredibly asymmetric, and that's the price that someone paid for the ticket. That's going to have a very heavy right tail. Even though it's a very continuous variable, it's unbelievably skewed, heavy on the right. We can look at basic descriptive statistics. We can look at the describe function, which is my go-to for descriptive statistics. It gives you appropriate output, whether it's a categorical variable versus a date versus continuous. And so you see, we're going to get the HTML version of that, which will be put right in your report in a nice format. And you really want to use the HTML and not the raw version, which would be DES or print of DES, because you'd like to get a lot more feel of the raw data. Now for ID, that doesn't help you so much, but for the age variable, this is the distribution of age with high resolution. You see some reference lines to help you judge relative heights, but you get the mean, you get the median, you get quartiles. Gini's mean difference is a nice measure of dispersion. The information fraction, number of distinct values, number of missing values. But the addition to little bitty graphics to your report is very, very valuable, I believe. So Describe gives you a very nice snapshot, and you see that the units of measurement is given here for ticket price, and it's set in a smaller font than the variable label and variable name. All right, and then there's some plots showing you how to get descriptives a lot of different ways, how to do bivariate descriptives. And let's look at extended box plots, because these are a lot more valuable than regular box plots. They have a lot more information. And the summary M function says, give me a box plot of age and a box plot of price stratified by sex. And then we're going to plot that. And so, and you see that these are interactive. So if you wonder what these corners mean, well, that corner is for females is the 0.375 quantile of age, which is 22.93 years. This is the mean, And then we have the median. Q.5 is the median, 26.99 years. So 3.75 to 6.25, that's the interval having 50% of the ages in it. And then you have your usual box plot corners, but you can read off what these corners mean by just hovering over the corners. Lots of other ways to display the data. And I'm just going to go to one other example here, which is we're using a new function in the GitHub repositories called moving statistics. So we're going to get a moving proportion of passengers survived as a function of price and passenger class. So we're going to stratify by passenger class. We're going to override how much smoothing is done. It's on data set D. And so this is going to get a moving proportion with overlapping windows of the continuous variable price. And since we said print equals margin, we're going to get a marginal note here automatically placed using Quarto syntax. And we're going to find out how the windows were constructed when doing the moving windows. They had a maximum of 31 passengers in a window, and the window was incremented by 1 year every time a new window was formed. So it's easy to get supplemental information that you don't want to necessarily busy up the main part of your report. Quarto excels with marginal notes. And I set by default to put all figure legends in the margin, which I think is very pretty and it makes things less busy. So this is our estimated relationship between the price that someone paid for a ticket, and depending on what class ticket it was, and their probability of survival. So you see that people that paid upwards of £100 and more seem to have a bigger chance of getting on a lifeboat, because the sex of the passenger needs to be taken into account here, and it's really not. There's not much variation in the price paid if you were a third-class passenger. Those are all fairly cheap tickets, but there is a lot of variation in price paid if you were a first-class passenger. And here we're going to get the probability of proportion surviving stratified by age and sex. And we're going to get that estimated a lot of different ways, stratified by sex and class, but using moving windows on the continuous variable of age. And this tells us how did we form those windows depending on like the sex category. And then we're going to plot the results, but we're going to ask it to estimate the moving proportions using low S without using our windows. It uses its own windows. And we're also going to use logistic regression. Logistic regression is really the best way to estimate moving proportions, assuming you remember to spline the age variable, and that was done automatically here. So if you looked at LR, that's a dotted line. The moving estimate is the dashed line, and the low S estimate is a solid line. They're in pretty good agreement. And if I were to trust one of those more than others, it would be the logistic regression estimates. So this is a way of treating age continuously, whether you're using empirical averaging or you're using low S or logistic regression. We're treating age fully as continuous. So any questions about that case study? All right, nothing in the chat, Ryan?
Nope, nothing yet, Frank.
Okay, and everybody speak up, make sure you get your questions answered or enter into some of the controversy that will come up. I'm not going to cover the R basics chapter because most of you will be past that. It may give you a couple of pointers. We'll go into report formatting. And so with figures, you have things to figure out, such as layout and size of figures. You have HTML tables to format. Placement, do you want something in the main body? Do you want it in the margin? Do you want it as a tab, or do you want it as an expand and hide paragraph? RepTools has a lot of reporting functions that will help you with this stuff. Then you have to decide on your overall format. There's two real choices. There's LaTeX, which is used to create PDF, and there's HTML. I'm really getting almost totally away from LaTeX now because I want to be able to have interactive graphics and I want to put things up as web pages. You can have multi-format reports, and there's some pointers in the RFlow ebook telling you how to do this. There is another format, which is Microsoft Word, and that is rendered fairly well with Quarto. I don't think it's quite as flexible as using LaTeX with PDF, but you can go straight to Microsoft Word. And then there's reporting that uses metadata information in a special way, which we've already mentioned a little bit. So there's syntax for figures with Quarto. The online documentation at quarto.org is extremely good. That backslash should not be here. So you would say C at fig dash scatterplot. That's going to be a cross-reference. The right figure number will be put into your sentence. This is how you make an R chunk. You know, this looks like R Markdown. It really is, and it's still using knitr. But in here, you can have labels, figure captions, short captions, figure height, figure width, and a lot of other stuff. So this is how you would put figure caption, height, and width inside the code chunk instead of putting it in the header of the chunk, which you can still do. And R Markdown is also now supporting this format. But look at this, this versatility here. Here's a symbolic reference for this figure. Here's a caption. Here's the height and width. I'm going to make this a 2-column figure. And I'm going to have subcaptions, and the subcaptions are going to be different for panel A versus panel B. So when I make 2 plots, as I see here, these are going to be left to right in 2 columns, and these will be the subcaptions that go with each of these right underneath them. And then the overall caption will go in the right margin. That's this. So that's very easy to do. You can also include existing figures as if they were drawn with R, but you include JPEG or PNG. And then there's built-in syntax for lots of things like enhancing the output or choosing where the output is going to pop up. So this says that this chunk, what it produces is going to be as a column that's going to be not in the body, but in the margin. It's going to be 1 inch high, 3 inches wide. We're going to make it a 2x2 matrix of things, and we're going to make a histogram, and we're going to make an HTML table with cable, and then another histogram. And so what we see here is a histogram, an HTML table. So everything that came from this chunk was put in the margin. And when that chunk is over, you go back to the body. We can expand the size of the area devoted to the figure. We can use more advanced layouts. So this says that we're going to have 2 figures on the first row and 1 figure that's wider on the second row. And you can also specify this as percentages. It's in the first row, the first figure is going to be 70% of the body area. The second figure, which is on the right, will be 30%. And you can do more advanced things. So formatting figures, you have kind of a whole new world of cool things to do there. Then there's these helper functions. Some of them I've talked about already, and let's talk about the ones I haven't. Make C note is for making a collapsible note using R code to make the note. So when the note is constructed with R code, you could use this. If you want to make a column marginal note, you can use make call marge, and this just creates our Quarto markdown that does this stuff. Make tabs is probably the most often used one. This will print objects or run code placing output in separate tabs automatically. Make mermaid is for making a mermaid diagram with R variable values inserted at specific places into the diagram. And you'll see a nice example of that. Lots of other things that are, some of them are special purpose. Here's an example where we're getting access to the GitHub RepTools functions. We're setting the seed, generating a random number and rounding it. And then we're saying make column marge tilde. So the first thing is going to be in there is a table. That's this. So the second thing is a directive. That's not to be put in the output. And that says that the table is going to be considered as raw and not HTML. So just putting raw anywhere in here makes tables rendered raw format, what we're used to seeing before we had HTML reports. And then the next thing that appears is a histogram, and then a plot of an empirical cumulative distribution function, and then a spike histogram. That spike histogram really needs to be much shorter than the vertical space devoted here. See, it wasn't very effective. It's too tall for a spike histogram. But you can see all these things appear in the margin and how easy it was to add them like you're building a formula, and this code is executed and placed in the appropriate spot for you. So these would be example of you're doing a report, you have some supplemental figures that you don't think are the main things, but they're kind of backup figures. You could put them as a collapsible text section, or you could put them in the margin. We already talked about this. And then there's a section on how to do automatic multi-output format reports, where you can sense which format is currently being run and have your things executed differently. So if HTML is being used, we're going to be using Plotly graphics, and we're going to translate all the ggplot2 graphics to Plotly automatically using the ggplotlyr function here. And if it's non-HTML, we're going to just leave it that the ggplot2 graphics are going to be left alone. They're not going to be changed. So that's an example of something that's sensitive to the format that will give you different output. And you could create your HTML and turn right around and tell Quarto to render LaTeX, PDF, and these will be executed appropriately. Quarto has a lot of facilities for conditional inclusion of stuff. There's special considerations for LaTeX and for other things, and special considerations and advanced usage of Mermaid. Now, HTML tables, this is what we're used to doing. And, you know, when you're constructing a table using this pipe, I think these are called pipe tables. Is that right? You can have things that are evaluated inside the table. So you can see here, pi came out because we had backticks with a little r. So tables can include things that are computed on demand. And then the table caption, if you have after the table, you have a colon and then a line here, that will appear as the table caption. That's a Quarto feature. You can do some special formatting by using cascading style sheets. And I have an example here you can look at. It's very easy to compose these things if you know just a little bit about CSS or find somebody who does. So in this h.css, I tell that to Quarto that this is here. And if I say this is, I think this is called fencing off. So this starts with 3 colons and it ends with 3 colons. Everything between there and there is going to be smaller by 2 levels. So smaller by 2 levels means it's going to be 64% original size. If I just said smaller, it's going to be 80% of the original size. So this is an easy way to make certain things small that you don't care as much about. So you see that all the text was smaller and the table was smaller. And then I have a style called quoted. So if you put a paragraph between quoted and the end of that, you see that it's centered, it's in blue, and it's in italics. So you can easily add special effects to your reports. All right, so that was our report formatting.
So Frank, I have a quick question about report formatting.
Yes.
So with our Markdown, I often use visual Markdown just to help make nice looking reports like you have here live. I was wondering if Quarto has any options for viewing your formatted report live while you're working on it like this?
The best Markdown previewer that I've seen is the VS Code editor. And so you saw the way that it previewed the mermaid diagram.
Mhm.
If your file was a .md file, you would have a preview button, and you'll have a live preview on your right panel, just like you had for that diagram. RStudio may also offer something like that too, but are you speaking of a small document in Markdown? Or are you talking about Markdown as part of a big report?
Just in small documents in Markdown, I hit the little compass in the top right corner for visual Markdown just to have a live view of what the finalized report will look like. But yeah, I'll have to look into Visual Studio. That
Yeah, VS
sounds
Code
perfect.
makes it super easy to preview Markdown, and it previews it beautifully. And I think it handles equations too, if I remember correctly.
That's excellent. Thank you.
Somebody's got a plug-in for just about everything for VS Code. Okay, any other questions about the formatting? Now this thing here is a special purpose thing where we can have mermaid be useful to include hover text. So you're looking at a diagram and you hover over part of the diagram and a table pops up. So that the table will render correctly, you have to make it into a Courier font family and preserve the white space. So that's a really beautiful capability. It's currently broken in Quarto. So I'm hoping that'll be fixed soon, but at the moment, that's not working. All right, analysis file creation. So this is my own personal preference, and I feel really strongly about this. And I can tell you the reason why. I'm pretty sure I'm right. Somebody has a long variable name like age in years or age in years at baseline, and they tell me they can understand what they're doing when they're viewing, when they're writing their code. That works pretty well up to a point, although I would still rather say label of age at some point to see what the label is, where it'll say age at baseline, and I would say units of age, and it would come up years. I'd rather do it that way. But where the long form really goes wrong, in my view, is when you get into specifying a model. I've seen some code where people have things like age at baseline in years, where they say restricted cubic spline parenthesis, age and baseline in years, comma, 4 knots. And then you interact that with another variable. And by the time you've composed your formula, the formula is almost obscene. I would be really hesitant to show that formula to anybody. Whereas if I said RCS of age, comma, 4 star sex, and so I have age interacting with sex in a nonlinear fashion, I can manage those formulas so much easier. So by the time you are using variables in a variety of contexts, it gets more and more clear to me that short names that really are unique and they're pretty descriptive are way more manageable. And then you annotate with your metadata. So you can have metadata coming from the database itself, which would be like you're importing from SAS, data, SPSS, that automatically brings in metadata. You could have metadata from external. So we're talking about labels, units, and other things. You can view the data dictionary. We've already done that. And then you can import all kinds of things, CSV, binary, loop over and import multiple files. And so there's some opinions here about directory structure and naming files. I don't like files to have dates in their names unless they're data files. Because if I put a date in a script name, that tells me it's already planned to be obsolete. And I don't want to admit that it's ever going to be obsolete. But data, sometimes it's good to have dates in the data file names, but although not always there. Managing things on GitHub, of course, is a good idea for scripts. So what about importing and creating annotated analysis files? And once I often create a separate script that's not necessarily a report. I often end up converting them to a report because I wanted to show it to somebody else. But sometimes I have a lot of creation steps, And I put that in and I have comments, but not really HTML and everything. And then I'll have a data table or data frame, and I will store that in compressed format saying save RDS, which is the recommended binary storage format for R. That's the name of the file you want to give it. And I want to use the most effective compression, which takes longer. And then that's the file I would give to somebody, or that's the file I would analyze myself using read RDS. So if you go through, if you're not dealing with a small file, or you have to create it in multiple steps, and you don't want to keep recreating that every time you run the report, having a create.r and storing it this way and quickly reading it in with read RDS is recommended. Updata is a good way to add metadata after you've imported things. And this just goes into this quoting function and how that really works. This is just taking a data set and adding a whole lot of metadata to it. You can see that, you know, it's a very natural format for doing that. And to me, it's much easier than doing something in a repetitive fashion. You're doing it more in a vector fashion. And we also created a function that says, yes, no variables have a common coding specified here, and we don't want to have to say that over and over. So we say yn once as a function, and we just use yn a bunch of times. These are variables we're dropping, so this will quote them automatically, specifying variable labels and units, and saving it. Now, this has special things for you to look at, like how to read external metadata. We saw a little example using Excel, how to read CSV files, how to process REDCap. Now, this one is one of the most important for us. And I've talked to some of you who have never heard of the import REDCap function, even though I've sent it around to the department like once a year for the last 9 years. It's really something you should always use when you're exporting REDCap data and you're not using the REDCap API. So if you're using the live interface to REDCap, that's a totally different approach. But if you're telling REDCap to export the data, like we're going to export to R, it creates two files, the .r file and the .csv file. This will clean that up because REDCap actually makes a total mess out of that. And a lot of your variables are stored twice, because if it's a factor variable, it'll store it under the name X, and it'll also store it under the name X.factor. And I just can't stand that. It makes me go crazy. So this will clean all that up. And if you don't give it the argument, it will find the last downloaded export and your current working directory and feed that in. Otherwise, you give it the name of the file. And so that's going to clean up so many problems and make your data set much better annotated and much more efficient and have many fewer columns in it. So there's just, I can't imagine any reason not to use this function if you've exported from REDCap. These are specifics about different things you'd be importing. This is how to deal with multiple files, and this is very powerful. So let's say you have a lot of files that ended in, they start with XZ and they end with CSV. I'm gonna get the list of all such files, and I'm gonna loop over them, and I'm going to read each one as a CSV file, and I'm going to store the file under this tree called capital X, which is a list that starts out empty. And each element of X is going to have a name of the original data file base name. So we're going to take the CSV off the name. So the base name names the element. This is a tree, or just call a list in R. So if you have 50 files you're importing at once, you do this into one big list, and then you can process them in a loop, and you can save that list unbelievably efficiently. So we had Sam and I worked for about 9 years on a clinical trial called ischemia, where each patient had about 65 case report forms. And we had like 7 years of follow-up, and put all of those 65 case report forms into one object. And that whole clinical trial in R in compressed form was about 2 megabytes. In SAS, that would be like 200 megabytes. So, and then you could process them in a loop. So this says, give me a list of all the variables appearing ever. Give me a list of all the variables that were in common to all the data sets. So I'm going to use the intersect function. Compute the number of variables across all data sets. So I'm going to say sapply of x comma length. For each variable name, count the number of data sets containing it. So I'm going backwards. You see the things you can do when your multiple data sets are in a list. It's amazing. And you can do it with really minimal programming. So that was this optional section here. This is just a little function that will find out the latest file matching this naming convention, the one that was last modified, and it will set that to F, and you can use that in any context. Things you do post-import, not really going to get into that. So that's analysis file creation. And so now we're assuming we've imported the data, we've got it annotated, we're ready for analysis and some sort of advanced data processing. So we're going to first find out where the holes in the data are. We already saw this example. So we saw a fully worked out example using the Titanic 5 data set. And this just goes into details explaining some of that. And showing you an example that was very much like the one we had. But we do have one other option here. We say predict number of missing equals true, and omit from the prediction the variable disease class because it's redundant once you know another variable in the data set. So what we're doing is now an ordinal logistic regression to predict the number of variables that are missing on a patient. So for each patient, we compute the number of variables that are missing, and the procedure automatically finds all the variables that are never missing and uses all those variables to predict the number of missing variables per patient. So what you see here in that result is here. So we see there's a significant association between the 20 columns that we use to predict the number of missing variables a patient has and the actual values of the non-missing variables. And we've got some various R-squared measures that tell you how strong the relationships are. C-index of 0.66. What are the key players? The key players are how long it was until they died and what disease group that's in. And here's the explanation for that. The biggest reason for missing was patients, and this is missing baseline data, patients were on ventilators. Being on a ventilator is a bad prognostic sign. So your mortality goes way up. And so if you're on a ventilator, your time until death is going to be shorter, and you're going to be more in certain disease groups that require a ventilator. And that's going to make the disease group and the time to death and the death indicator be strong predictors of missingness of the other variables. That's just because most of the missingness was due to ventilator. You can't interview a patient, ask them their quality of life because they can't talk if they're on a ventilator. So that's more of an advanced analysis of missingness. Now, data checking gets us into something new. Most people are pretty familiar with the kind of checks that you run. You have essentially two kinds. There's sort of valid value checks of individual variables, and there's cross-variable consistency. So what we want to do is to check and report with minimal coding. This should not be repetitively coded when you can factor out the commonalities. And we want to produce listings, we want to produce summaries. So there's this data check function in the GitHub repository, which comes in when you say get rs of rep tools. We're going to get access to data table, the stress echocardiogram data set from our web page. And I'm going to call it a short name W, make it a data table. I'm going to add an ID. We may need a patient ID on the data set. It did not originally have one. And I'm going to make up a site variable just so we have an example of what it looks like when you want to report by clinical site, like different hospitals. Now, this is just one of the many powers of the R language. So this says expression. That's a special unevaluated syntax. An expression can have multiple arguments so that you're creating a vector of expressions. So our first expression is age less than 30 or greater than 90. We don't expect that to happen very often in our data set. If the person is female and the maximum heart rate is 170, I'm just making this up. Let's suppose that's an unexpected outcome. If the base ejection fraction is between 72 and 77, we may want to do some special look at that. Or if it's greater than 77 or greater than 99. And so you can see you've got range checks, but you also have consistency checks with the same syntax. So if this is greater than 250 and the maximum heart rate is less than 160, we might want to flag that. So then we just run these checks through data check. They're executed one at a time to see whether they evaluate to true or not. And we treat the ID in the site specially. We're using an option and we're outputting HTML. So you get a report for each thing you're checking. These are the observations with the ID in site for when age is less than 30 or greater than 90. This is when you had female for a maximum heart rate greater than 170, base EF between 72 and 77. These all have the same format. And the title here defines what the check was. And then you have a different kind of output, which is by ID in site. So now you can see the patient ID is in sequential order. So you'll have all of the suspicious data for one patient all together. And you have site here. This is the check that was flagged. And the values that made it flagged was female. So it gathers that gender was used here. And 171, which it looks up the max HR. So these are the values that triggered this to be true. This is somebody who's younger than we expected in the data, and that the exact value was 29, and so on. See, it all has similar format. And then you can see a summary. And the summary here is how often did we flag an observation for age? There were 9. How often did we flag for this cross consistency check? There were 3. The main point of this is once you look at the code for this thing, it's not very long, but it does things in a loop so you don't have to. So if you find yourself having a lot of if statements, just think about putting it in a vector of expressions, looping through that, and then doing the same thing over and over, but you're doing it with only one little set of code. That's exactly what data check is doing. So there's a moral to really this whole session, which is if you're doing something more than once or twice, you need to factor it out. You really, really don't want to write the same code, especially more than twice, because you'll end up fixing one of them because you're making improvement and you'll forget to fix the other one. So you need to fix it once. So any questions about data checking?
Frank, all the tabs that appeared at the bottom of the interactive report, is that that comes from data check automatically, or did you need to format those?
That comes, data check uses the RepTools functions. And in one of those functions, I briefly went over, it was called make tabs.
Mm-hmm.
So you'll see inside data check, it runs make tabs parenthesis stuff. And it saves the output as you are executing it. Then it adds the 2 reports at the end here as data. And then it calls make tabs, which is defined in reptools.r, which comes in from doing this. So make tabs has to me been a very handy function. Otherwise, the amount of markup you would need to use with Quarto is going to be a little repetitive, and it won't be dynamic to your data.
Yeah, it looks excellent.
Yeah, so look at make tabs. It's just a few lines. Okay, data overview. We've already covered most of that, but this first section is new because part of overviewing data is to describe how observations are filtered. Now, filtering could mean a patient starts a clinical trial and didn't finish. It could mean somebody is screened, but they didn't pass some screening criteria, or it could mean that you excluded observations due to missing. And so the displays we're going to make will apply to all of those things. So if you're talking about observation filtering, you want a diagram with insertion of computed counts. And the consort diagram for clinical trials is a established format, and we'll show how to do that. And mermaid is a way to do that plus a lot more, but it won't meet the consort picky formatting. So New England Journal will send it back to you and say, use plain rectangles as consort diagrams do. And then the data about data is what we already talked about in our data snapshot. So let's just talk about the filtering. There's a wonderful package in R called consort. And if you set up your data a certain way, you can easily get your consort diagram. So this shows how to use data table to simulate a clinical trial real easily. So the ID variable is going to go from 1 to n is 1,000. The age is going to be a rounded random normal thing with a mean of 60. Pain is going to be an ordinal from 0 to 5, sampling with replacement from those 6 integers. History of medication is going to be a randomly chosen 0 or 1, no or yes. So we're sampling with these probabilities with replacement. And then we're going to set the consent status to those that were not excluded at screening. So for those that were at least 40 years old and had some pain and they had no history of using a certain medication, only in those people do we need to define their consent. Otherwise, they don't need to consent to be in the study to be randomized because they already failed the screen. So this variable will be missing if you failed the screen. Otherwise, if you pass this variable will be computed as 0 and 1. For those that were consented, only in those do we need to calculate whether they were randomized or not as a 0-1 variable. We're going to say that your probability of being randomized is 0.85. So if you did not consent, the randomized variable would be missing because it was never defined. We're going to add treatment and follow-up only to randomized patients. Otherwise, those variables will be missing. And we're going to add follow-up data, but we're going to lose some people along the way. So that's what our simulated clinical trial looks like. And this is how we set up things for use with consort using the consort plot function. So it uses this argument called orders. It has your data R, it's called R here, and you give it these various things it expects to see. And you can also define optional side boxes. And this is your allocation variable. It's called TX. And you have labels. And so you'll get your classic, exact, correctly formatted consort diagram with some additional headings that you don't have to put if you don't want that. And you can control a lot of colors and other things. Now, I think it's actually more flexible not to use their default format, but to set up your data in such a way that's more like the way we usually set up data. And you can use the consort functions like add box, add side box, add split when something is stratified by treatment A and B. And then I can add counts. I can add all kinds of things. I make little functions like this function counts by something. And then by adding the boxes and piping all this stuff together, I can get the same thing as I had before. And so that's just a second way, which is probably the one I would use for doing a consort diagram. And you can see how the values of certain things like counts are inserted into your stuff. And the H function just pastes the parenthesis n equals parenthesis onto the count. So when it appears here, it's going to have the consort format with the parentheses. So that's all pretty easy. What if you wanted something more general than a consort diagram? You can use mermaid, and this is really using features in rep tools and the built-in handling of mermaid. But you can see what's different about this one is the mermaid code is not in a chunk by itself, but the mermaid code is in quotes. So it's just a big character string called X. So when you say X, and this is a mermaid comment symbol, so you add a comment to specify the caption for the figure. And this is the notation used by knitr. So knitr has a function called knit_expand. And so when you say knit expand, and the thing I want to expand is the value of this will be inserted into the caption dynamically. We're going to give a label. We're going to have a flowchart type of diagram. And we're going to say S is the node for screened. And we say parentheses n equals brace n0. So that's going to be a variable to be inserted using this brace notation that knit expand implemented. And it was interesting that the UA who wrote knitr added this capability when I requested it about 10 years ago. It was nice to add that. So you see how we're inserting variable values in a very natural way. And then the way you pass those, you say make mermaid, and you pass them by name, and you just give it what is that representing. You can use all kinds of functions to create the values, but we're going to use count here for a lot of them. And some of them are just raw counts. Some of them are stratified by things. And at the end, we're going to say how many people had the outcome variable assessed, so it's not missing. So when you pass this X to make mermaid, and then you pass all these other arguments, those other arguments are looked up and they're filled in dynamically. So you can see these are variables, straight values, single numbers that are inserted. And this is what it looks like when you get the result. So I inserted something that was a little bit complex there. Yeah, question? So you see how I get the numbers in the parentheses, and then there's a branch. So that branch came because now I'm got it to separate by A and B. But this is a function that makes it automatically branch by treatment like the consort package did. This is a little more advanced programming and dealing with parallel nodes. So, but it makes it, once it's done, it makes the creation of parallel nodes really easy. So now you can say that TX counts as a parallel node because it's going to be left as treatment A and right as treatment B. This is going to be a parallel nodes. These are parallel nodes. And we use a special syntax called callback, which means if you hover over one of the nodes, you're going to pop up a table for extra information. That's what's currently not working in Quarto. It does work for some browsers. It doesn't work for all browsers. So this is how I use Make Mermaid now, and I'm doing it inside a data table. So I can access any of the variables inside that data table without using any prefixes here. So I say get inside data table R and stay in there. And within that context, run Make Mermaid. And I'm passing the information, including some of the information is parallel nodes, and a parallel nodes is just like a vector instead of a scalar. And we're going to save the generated markdown code for another use. So this is what you get. So this is supposed to hover more information. It did move when I put the mouse here, but it didn't bring up the table I asked for. But you see that you can make some pretty nice diagrams. It's just that you have curvy lines and things that consort diehards will not like, but you can use this for a lot more than you would use in consort. So I think this is just a really nice way to look at data filtering, whether it's clinical trial qualifications or just filtering on missing data in a regular analysis. So that is data overview. So we are now up to descriptive statistics. So the describe function we've already seen. It's a good default starting place. And then for categorical variables, you can make frequency dot charts. For continuous variables, you have a lot of choices, such as spike histograms and extended box plots. What about longitudinal data? We have a lot of choices. You can make raw data spaghetti plots, one strand of spaghetti per patient. You can choose representative curves, or you can show ordinal transitions and states. And what if you have time to event data? You can show event charts and timelines. And what if you had relationships? You can show graphical correlation matrices and variable clustering. So we've seen some of that already. And this is what you can use to pop something up into a separate window or in the view window in RStudio. This is how we can make some multiple tabs. This is going to make two tabs because this plot function produces two plots, and it puts them in a list of two elements. The names of each element are shown here. So we see the categorical variables plotted separately from the continuous variables, which are using spike histograms. Just descriptive statistics. Here we're using make tabs, but now we're using a graph type of plotly, which some of my functions respect that option, and they'll automatically make interactive plots in a different way. So this is going to make two plots, categorical and continuous, but now you see a lot of information. So now you see the number of missing values, you see the variable labels and not just the variable names, but you see these are just proportions in each category, and you have it stratified by the different levels of the categorical variables for the different variables in your data set. For continuous variables, you get a lot of information because when you hover, you're going to see the quartiles, the quantiles, mean, the missing, number distinct, information content, a whole lot of stuff. And you see the label, basal heart rate, and the units of measurement is in a different font beats per minute. So when you hover over the leftmost tick, you see a lot of information. Otherwise, you just see what's the frequency count, which is 16 for a heart rate of 106. So I would say these are very descriptive because they're showing almost all the raw data, at least in a univariate fashion. And we can do this in so many ways. So make tabs, you can give it, let's say the first tab is going to be blank. So we say blank tilde blank. That's going to make an empty tab. And there's an option to do that automatically. And it's good to have an empty tab to start because that means the empty tab shows, which means nothing shows. And you have to actually click something to make anything show. So that's how you do that. Table 1 is going to be an advanced HTML table. A categorical variable plot is going to use the plot function. And the caption function is just going to pass a caption to this thing. And the fixed size function is going to pass a width to that. So it's real easy to add extra information. And then a continuous variable plot here. And we say wide equals true means we're going to let the plot be wider than normal. So you can see that's why it's moved over here. So if you look at table 1, you get a pretty advanced table, and it's got too many p-values on it, which is for another day. But you see the variable label, units of measurement used specially, and they populate the table. And then you see your median is emphasized as your measure of central tendency, and your 25th and 75th percentiles are subservient to the median. So it's a pretty long table, and it has footnotes to tell you what some of the symbols are. So this is the second real tab. That's our categorical variable plot. We've seen things like that already. And then you have your continuous variable plot. We saw something like that already. So you see how easy it is to put things into tabs, make names for the tabs. You see the names are what's to the left of the tilde here. So you could make a whole lot of tabs. Here is making a spike histogram grouped by ECG, 200 bins inside of data table D. So this is how you use a variable that's inside a data table without using a $sign. Now, when you get into longitudinal data, there's a lot of other ways to do things. And what we're doing here, I think we're creating some longitudinal data, and then we're going to cluster the data to create representative longitudinal trajectories. And so these are representative trajectories for patients that had only one data point. So there's no lines to connect. So you can only cluster them according to their average, sort of. For patients, or at one point, for patients who had 2, 3, or 4 measurements over time, these are clusters of representative trajectories of those patients. You can see the scales to really large data sets. And once you get up to 8 to 10 points per patient, you see you're filling in a lot smoother curves, and you're clustering them on like the overall average and on the shape of the trajectories. So these patients were called similar overall and put into trajectory cluster 3, and they were put in time distribution 1 because of the schedule in which these measurements were made. So that's just a way to display high-dimensional longitudinal data without too much trouble. And you can pass that to make tabs to separate it by the sample size per patient. You have special plots for longitudinal ordinal data, which I'm not going to spend much time on, but you have a lot of choices there, such as multiple event charts and transition diagrams to show probabilities of state transitions as you go from time 1 to time 2, time 2 to time 3, time 3 to time 4, and you can hover to see the details. So we use these kind of charts in COVID therapeutics research quite a bit because a lot of the outcomes are longitudinal and ordinal. We use this even more. The clinicians really like these stacked bar charts that show the level of outcome per day separated by female and male. We usually separate it by treatment A and B. Special charts for adverse events, continuous event times, all sorts of event charts showing relationships. So relationships can be shown by correlations and by variable clustering, among other things. And we're using this new function vclust with a capital C that's in RepTools, and it automatically produces these tabs. So you see a correlation matrix of all your variables, and you see that the height of the bars is proportional to the correlation. All the bars go up regardless of whether it's a positive or negative correlation, but they're color-coded by whether it's positive or negative. These are much more accurately perceived than some of the other charts you'll see with R packages. They try to use heat spectrum to denote the level of correlation, but I don't think that's nearly as effective as the heights of the bars. And the other thing that's produced is a variable clustering diagram to understand which things tended to be correlated with which other things. So that is data overview. Any questions about any of that stuff? So data manipulation and aggregation is where you get into a lot of interesting things, and sometimes they're a bit challenging. So we have data table, which is really, to me, what should be at the center of data manipulation and aggregation. And once you learn data table, it opens up huge horizons for using R efficiently and clearly. What I've tried to do in this chapter is to give you the most commonly used things with data table all in one place to make it easier to learn. So we'll be subsetting, modifying variables, recoding, reshaping, And what you really need to know is this diagram and the restatement of it in the chart below. If DT is the name of a data table, and a data table is also a data frame, let's say it's a data frame called D or W or whatever we've been using, whatever you call it, the name of it, what are you doing on the rows, which rows are you operating on, what do you want to do with those rows, like with regard to columns, and then grouped by what. And then there's a lot of extra arguments. So I've expanded that a little bit with this chart. So when you say DT left bracket, this means to enter the environment of DT. So everything you're doing around here is going to be in the environment of DT. So this is like in data frames, anytime you've seen with, if you say with data frame name, parenthesis, you're entering the environment of that data frame. This is very similar to that. So everything you're doing now is in the context of this data table. And these are the arguments to the, these are the rows, columns, and whether you're doing by processing or matching on variables. And so the rows are the rows to fetch or change. The columns are the columns to fetch, or they're the columns to redefine, or the columns to create new. And then you can have a third piece, which is grouping or matching. Then you leave the environment, and what are you left with? Well, that depends on what you were doing here. So if there was no colon equals, you might just print or plot a result or assign the result to a new data table. If there was a colon equal, that means you're changing DT in place. You're either removing, recoding, or adding a new variable in place without making any new copy of anything. So that means change in place or add in place. So I hope once you look at this long enough, if you haven't been exposed to data table yet, you'll see what really is driving the system. It's just incredibly well conceptualized. It has an amazing team working on it. It's got some of the best quality control you'll ever see, and it has no dependencies. So you'll see Tidyverse has an unbelievable number of dependencies, and things get really hard to maintain as new versions come out over long periods of time if your project lives a long time. Data table has no dependencies. So this is how you print the second row, how you print the second, third, and fourth rows. This is how you fetch rows for November. This is how you fetch rows where the month has MB in it. So the month is like MB. This is where it has MB in it, ignoring the case. Two conditions are satisfied. We're retrieving one variable. We're retrieving two variables. You have dot parenthesis. Looks a little new to you. We're going to get the ith column where I is a variable. So you have to do that differently than data frames. You have to have something like a dot dot here. So this is to note that that's not an absolute column. It's a variable. This is how you would retrieve a variable by character name. You can also do it this way. This is how you get the last row. Dot in means the max, the number of observations. This is how you get the last row at each age. And while you're doing it, you're going to sort it by age. This is how you get variables between BHR and PKHR. This is how you get all but those variables. This is how you run a lot of lines of code within D. So look at those, gives you a good idea of things that you'll do very often with data tables. And here's an example where we take the character string x2 and we change all of the character values to uppercase. Anybody have a question?
Can I ask a quick question, Frank? This is
Yes.
Kathy.
Yes.
If you scroll up a little bit, to keep going a little bit more. Yeah, so when you have the key by equal age, you have to do a set key statement before that.
You do not.
Okay.
So if your data set wasn't sorted by age, you could still process by age, but it would come out in the original age order. But this will, key by will sort it while it's doing this. It'll come out in age order.
Okay. All
You
right.
don't need
Thank
to,
you.
yeah, you don't need to previously declare that. So this is how we change an existing variable. And this is how you might analyze a subset. Or let's say we could just operate on one variable within the whole data table. We're going to have another name for the data table. It still occupies the same place as stress echo. Make it actually, this will create a copy because it's a data frame at this point. This makes it a data table. This will operate within the data table to give you the describe output on just the age. This will give you describe on age and gender. And there's a ton of variations on that I won't really go into, but this is what we really need to look at a little bit more. This is how you change the names of variables longhand. This is how you do it with the more automatic quoting. So you have the old names and the new names. They're both vectors. Or you can have a named vector and turn that into two vectors. This to me would be a little more natural, but I would rather use the updata function probably. You can create your own rename function to do that. There's just a lot of ways to do it. You can do things with variables that satisfy certain naming conventions and do things on groups of variables all at once. That's very easy to do. Now, the updata function has a lot of advantages, as I mentioned. One of those is sometimes your source of data did not have units. So REDCap used to have units, and it was taken out to simplify REDCap. And I wish everybody would join me in lobbying Paul Harris to put units back in to REDCap because it's very helpful. But if your units are in brackets or parentheses in your labels, if you use that convention, this will move them out of the labels into units and then make your labels shorter to remove that stuff. So this is a way we handle it on importing some data. This is how you create a new data table, because we're not using colon equals, but we're using, and we're assigning it to Z. So the new variables are BMI and BSA. We're adding one new variable in place. So you don't have Z over here, you just have D bracket. Give me a new variable in place. Add two new variables in place. So you have to put this in backticks. And that's the language data table uses when you want to add lots of variables sort of in vector fashion, or you could quote them with .q and create two new variables at one time, or you just use updata and do the same thing. And updata operates efficiently on data tables. Compute something different that requires a different formula for different types of observations. So we're just using if else in our creation formula. And this F case is in data table. This is a wonderful function. So we're gonna say if the person is male, we're gonna use their height. If the person's female, we're gonna use their height times 1.07. So F case is a very flexible function for recoding that I think is going to be one of our top functions for that use. There's some specialty things here. And this is more on recoding variables. So this is how you would have a factor variable that has lots of levels, and you want to group some of the levels into fewer. So you got multiple ways of doing that. Quote them as if they had quote marks. We've got levels A1, A2, B1, B2, B3.
就对比一下。
Somebody please mute your microphone. And so we're going to recode A1 and A2 both as A, and B1, B2, and B3 all as B. So that will do that. So now you're going to have 2 levels instead of 5, but this is more elegant. This is built into R. Levels of data table variable named X is going to be a list where all the levels A1 and A2 are going to go into level A, and B1, B2, B3 go into B. So that is an elegant way to group levels, and you can also use that format with updata. So that's a nice sort of hierarchical syntax. You can do things with substrings, and let's get more at F case. So let's look at this example here. It's a good one. So we've got a data table called D, and we want to create a new variable inside that data table without copying anything. And if death is true, the new variable is going to have a value of quote death. That's going to take precedence. If the person did not die, but X2 is either stroke or MI, we'll have X equal to quote stroke / MI. If that did not happen, and this did not happen, but X1 is quote symptomatic, then the output that goes into X is going to be quote symptomatic. And the default, if none of those were true, is going to be quote none. So this is the kind of recode we do a lot of. And I think the F case function is a particularly good way to do this. And that's a function in the data table package. Lots of other ways to do table lookup and recoding. We don't have time to go into those. You can do hierarchical multiple level recoding. Well, don't really have time for that, but I think you can see the power of data table, and you have so many choices in how you recode things. You can also do operations on multiple data tables, such as combining data tables vertically or horizontally. And let's see, I just want to go to one more advanced example, but this is just showing you how to go from tall and thin to short and wide. So you have a data table that's tall and thin. You use dcast, very nice syntax for making it short and wide. You reverse it using melt, and these are special high-speed data table functions. You get the result that we started with. And then when we get to longitudinal data, I'll show that more advanced example. I'm not going to spend much time on summary statistics, because for one thing, we're running short on time. But this chapter is a pretty big one, and there's a lot to it. And the take-home message for this chapter is, when you're summarizing things, try to write a function that's the simplest function you can that would summarize one patient. So if you were not grouping on anything, how would you summarize one patient or one group? Let's say the males. How would you summarize the males? And later you want to do it for both males and females. Write a function that will summarize just the males or just the females. Debug that function, get it really working, and then use it inside data table in a repetitive fashion to do both males and females. You'll see a lot of examples using data table here that are really cool. And when you take a little time to look at it, you'll see that this .st notation opens up a whole world of options. That means all of the columns in the current data table. And you can also subset which columns you're currently referring to. And then we're going to do some processing on all of those variables the same way by making a table. And we're going to put those tables all together like this into one big HTML output. And there's lots of ways to do that. Special things are needed for functions that return two-dimensional results. So that's getting a little more advanced, but the data table coding is actually very, very elegant. And this will be a way to tell it which variables to operate on And then you're going to apply the same function to all the variables that you listed here. So you can do things, and that function could be returning more than one value. So there's really no limit to what you can do. This is really cool, I think. If you use the cube function, what we're going to do is calculate the mean basal heart rate. That's just a little function I wrote above that takes away missing data. This is the number of non-missing values. So we're computing two things. We're going to do it by gender and history of myocardial infarction. ID equals true means we're going to save a variable grouping that tells us how the grouping was done. So when you use cube, that means do it all possible ways. So we're going to see it by gender and history of MI like we ordinarily would see it. We have a 2x2 table here. But we're also going to do it by sex, ignoring history of MI. And we're going to do it by history of MI, ignoring sex. So these are marginal summaries. And then we're going to ignore both, which means this is the grand total, the grand marginal summary. So cube means do it by every margin of this cross classification plus the original cross classification. And that makes that sort of high dimensional summary very easy to do. So in the limited time available, I've got to be kind of selective. And I'll just point out a couple of things from each of these chapters. Data table is incredibly powerful and fast for merging data. And this is the real built-in syntax for data table to do what's called a left inner join on the variable named ID. So that's what most people would say is a standard merge. And you don't have to like that very concise notation, because you can still use the merge function, or you can use the merge function with a capital M in the HMIS package. So this says to merge the baseline data with the longitudinal follow-up data on the variable named ID. And this actually is using data table merging inside of it, so it's very efficient. But you get a report telling how the merge went, and you could merge 30 data sets here, and it would give you a long report and merge them all. So how many variables were in the baseline data set? How many variables were in the longitudinal data set? How many observations? How many observations are in the merged data set? So we had one person in one of the data sets that was not in the other. So by this default setup, we have 13 patients. The merged data set has 4 variables. Some of these were overlapping. And then there were 4 unique IDs in L. 3 of those are in the first data set. So there's a new person that did not make it into B. And the merged data set has a total of 5 unique persons. 4 of those were in number 1, and 1 of them wasn't. The number of unique IDs in any data frame was 5, and in all data frames was 3. So that's just a way to get a report that helps you know that your merge was successful in the execution. Now, just to whet your appetite about merging longitudinal data, this chapter has a lot of useful stuff in it. So what it covers is different formats that you might have for longitudinal data. You might have a hierarchical tree or list. You might have a short and wide data set, or a tall and thin data set. And then you have different things you'll do on these different things. Like you might want to do a last observation carried forward when you have a uniform number of rows, but some of the values are missing. So that there's a function in data table that does that automatically. But sometimes you have a variable number of rows and you still want to carry forward by actually adding new rows. And there's example code in this chapter that shows you how to carry forward by adding new rows that were never in your data set. Find first observation meeting certain criteria and using functions that count. And so this goes through various ways to do these things when you have longitudinal data or serial data. And one of the neater things is to think of it in a more general way. So sometimes we'll say, we'll use data table notation, and we'll say, did something meet a certain criterion? And instead of that, we'll count how many times the criterion was met, and we'll do an if statement on the count. So see if this makes any sense here. So this is a function. Sam was the one that put me onto this kind of coding. And this will calculate the number of times something has occurred on successive visits or successive observations. And as long as the string is intact, like here, the string is intact here, then it's broken, you start over. You have consecutive values here that are the same, and then you start over. What is the number of times that something has been a 1 consecutively? See, it's been a 1 once, it's been a 1 twice. Now you start it over because you're a 0. You start over, and you start over every time it goes to 0. So every time you start over, you're gonna say, well, it's no longer consecutive. So this is the number of consecutive observations in which a condition X was satisfied. And so we can say, using data tables in a very natural way, give me the in our observations, calculate for me what was the first day for a patient. See, we're doing by ID. What was the first day for a patient? The minimum of the days for which, or such that. So this means such that the number of consecutive times that Z was greater than 0.5 was equal to 2. So if you're at the second Z greater than 0.5 in a row, that's going to be true. And if you went on to do it again later, we just want to know the first day in which there were 2 consecutive occurrences of Z greater than 0.5 for that patient. So this helps you kind of read what that syntax is doing, hopefully motivates you to want to use that syntax. The limit of that for me is a non-equi-join or overlapping join. And so this is a more advanced example because data table has this function that's amazing called F overlaps. This is a slightly less advanced example, but the more advanced one is here. So what we're trying to do, let's see, where's the advanced one? Oh, this was the advanced. Consider an example where there's an events data set E with 0 or more rows per subject containing start and end times and a measurement X, representing the daily dose of something given to the subject. And the dose was given from time S to time E. The base data set B has 1 record per subject with times C and D. Compute the total dose of drug received between C and D for the subject by finding all records in events data set E for the subject such that the interval CD has any overlap with the interval SE. For each match, compute the number of days in the interval that are also in the other interval. Multiply this duration by X to get the total dose given in the C to D interval. And this is the logic that will do that. You see the programming is minimal. Figuring out how to use F overlaps is the key. And you see that the variables that you're doing a fuzzy match on, they have different names. Low and high, start and end. They're different names in different data sets. So you tell it by.x and by.y. That's going to do the fuzzy overlap merging so that you can calculate the elapsed time and the total dose, the sum of dose times the elapsed time. So a lot of stuff we didn't get to. Maybe we'll have a follow-up session at some point when you've had time to recover for this, but I hope you'll look at the other chapters and let's see if there's any questions here.
Frank, I have a question. Well, first of all, thank you so much for putting all this together. This is, like you said, it's going to take a long time to process through and assimilate some of this. But I'm really interested in the make tabs function. I really think that can just clean up a lot of the code. Do you know if is it usable in R Markdown, or is it only in Quarto?
I think, and don't quote me on this, but I think the syntax for making tabs in the basic Quarto is different from the syntax in R Markdown. So what I would recommend you do is to take the make tab source code, which is just a few lines, and make a new version of that, or make a new option. You could also fork that from the GitHub and work on it. Make that a new option that emits the R Markdown syntax rather than the Quarto syntax, if they're compatible in other ways. And that way we'll have, if you use that new option, people will be able to use either system.
Okay, yeah, I'll give that a shot. Thank you.
I think Quarto is irresistible though, and it's so easy to edit a few lines and move your project into Quarto from R Markdown. And I forgot to mention totally, R Markdown works, it's built into RStudio, but it also works fully from the command line. So you would say Quarto render myreport.qmd. If you were doing a book with a lot of chapters or a big report with a lot of chapters, you would say Quarto render, and that would render all the chapters and put them together in an ebook. So this is strictly from the command line. It doesn't have to be under RStudio.
I might have to give that a shot as well.
All right. Any other closing questions?
I use the child R Markdown file in my report. Can I use the similar thing in Quarto?
Yes, Quarto, you can do the same thing because you're using knitter for both systems. You can use that because there's a knitter function call that does it, but Quarto also has a built-in syntax for that is just a little more elegant. So you can do it the old way or the new way within Quarto, I believe.
Okay, thank you.
If you ever get an account on Hypothesis is an annotation system, and you can annotate and put questions right on the material for our flow, the R workflow. So you'll see a comment somewhere in the material that shows you how to join Hypothesis to the HTML file you're looking at for highlighting or for asking questions or entering comments. Well, I appreciate everybody being here, and I hope you find this stuff useful. Follow up with questions. Send me an email for the parts that are unclear. You'll probably give me a lot of ideas for improving the material and adding some examples you'd like to see. So your feedback would be most welcome. Thanks.
And if anyone would like to take a look at the HTML report Frank was showing us, there's a link to it within the invite email I sent out. And if you'd like to see a copy of the recording we made, feel free to reach out to me and I'll add you to the box link.
Thanks, Ryan.
Thanks, Frank. Thank you all for coming. And Frank, if you ever want to present the rest of the R workflow, we'd love to have you.
I'd love to do it. Talk to you later.
Yeah, have a great weekend.